Welcome back. Today, we're going to talk about what is the goal of all this. We covered Laplace transforms from the basics using the table last time. Today, we're actually going to get into what did that mean for our mathematical models. We've done Bobati. We're trying to find a response. How can we actually do that? So the goal of using Laplace transforms is to find the response. And again, that's basically, this right here. What is the actual equation for that output response? I can use the transfer function for that if there's no initial conditions. But if I do have any initial conditions, like a starting position, starting velocity, this is where we need to use the formal Laplace transform to get all those terms out. So our goal is first to obviously, well, not obviously, always put the differential equation in standard form. So that's on the equation sheet. We covered that last time. For a second order, we're trying to get s squared plus or y double dot all by itself. Then what we're going to do, and I'll talk about this on the next slide, is we're going to take the Laplace transform of every term in the differential equation and incorporate the initial conditions. So that's this thing, which I'll explain on the next slide. So we're going to do this for every single term. This is where we use the initial conditions. I'll talk about that. Once we do that for every single one in the equation, we're going to put it all together. We're going to solve the Laplace transform in terms of the output. And then we're going to separate into partial fractions using the roots and the poles. And lastly, once I have it all separated out, we find our constants. We can then find that dynamic response by taking the inverse Laplace. So our goal at the end is to get it back to the time domain. So now we can find y as a function of time. What is that function? Now, there are a lot of steps to this. We're going to go through it today. That's what today's class is all about. So we're going to start with, we already know standard form. I'm going to start with 2. Then we're going to do an example problem. We're going to look at how to use partial fractions, and we're going to work our way to the end. Okay? So before we solve a problem, here's that equation, which is on the equation sheet. I'm going to give you a quick example. So basically, what this is showing us is Laplace transform of anything with derivatives. So a Laplace transform of some kind of function with derivatives. We work it out this way. So we're going to have s's. And let's start with Laplace transform. So if I had an equation, let's just say it started with 6y triple dot. So let's do the Laplace transform of 6y triple dot. You know what, I'll do that. Just to be a little bit more consistent. 880. So we're going to take, once I have it, my mathematical model, we can take the Laplace transform. So in this case, to use this equation right here, n is the number of derivatives, basically, like the order. So what is the order of y triple dot? It's third order. So in this case, n is equal to 3 because I have a y triple dot. What I like to do always, the 6 we can just pull out of there. So I can do 6 Laplace transform of y triple dot. Now, I can also rewrite this if you want, if it makes a little bit more sense to you. This is going to be 6 times Laplace transform of, this would be d cubed over dt cubed times y, which is a function of time. Okay, so that's another way that we can write it, right? I got 3 derivatives on here, triple dot. So once I have the model, let's say there are initial conditions. That's an important part of this. So at time 0, y is equal to 3, y dot is equal to -1, then y double dot, acceleration at time 0 is equal to 5. So those are my initial conditions. Therefore, I must do this method. And this method works all the time. But I especially need it for initial conditions. Have I lost anybody up to this point? Okay, now we're going to expand on this. The first thing I'm going to do is I'm going to have a 6. Because everything is going to get multiplied by that constant. And now we're going to actually expand on, okay, what is the Laplace transform of y triple dot? First thing we're going to have is s to the n. We already said n is equal to 3, so we're going to have an s cubed times our function, s cubed times our function, which in this case we're saying is y. So now we're in the s domain. We have an s cubed times y. And now we go to the next one. So that's here. Now we're going here. So we're going to have a subtract. It's always, all of these are subtracted. Once I have that first one, everything else will be subtracted. We have s to the n minus 1 or 3 minus 1. So we get an s squared. And that gets multiplied by my initial condition with no derivatives. So what should I use? Which initial condition doesn't have any derivatives? What is y at time 0? It is 3. So we're going to multiply that by 3. That's what this f at time 0 is. Obviously, we're just trading y's for f's. And then we just keep moving on. So we have another subtraction. You can probably see a pattern going on now. So I have s cubed, I have s squared. This is just going to be s times. Now I'm going to my first derivative. So we're walking up in the derivatives here. We're walking down in terms of s. This would be a -1. And then the last one, because I do have another initial condition. So the acceleration at time 0 is equal to 5. This is where this last one comes into play. So really, I'm just walking down s's, but I'm going to have a final term with no s. It's just going to be, you can think of this as like the derivative. So n, which is 3 minus 1, so that's 2. That would be like f double dot at time 0. That's the derivative right there. So that would be just the subtract 5. And we can then take this multiplier. So we can just get all of our stuff together. The negative times -1 gives me +6. And that would be our Laplace transform of 6y triple dot with the initial conditions given. Now, what happens if all my initial conditions are 0? This is 0, this is 0, this is 0. So I'm just left with Laplace transform of 6y triple dot is 6s cubed times y. That's like our Laplace, or that's like our transfer function, right? Transfer function, again, it's Laplace transform. It just doesn't involve initial conditions. Okay, let's do another one. And then, well, actually, questions right now before I do the other one. Anything? I think the tricky one a lot of times is this last one is this, I'll always have just a constant at the end here when I do Laplace, unless this initial condition is 0. But there should be a term without an s at the end when I'm doing this differentiation. Okay, let's do the second one. So Laplace transform, let's say we have a 2y double dot. So 2y double dot. Again, I can take the 2 out of there. And now n is equal to 2. Want to make sure I've got that 2. That's going to be my multiplier for everything. And now when n is equal to 2, we get an s squared times my function. That's the first term. Now we have everything is subtracted after that point. We have an s to the n minus 1, which is just 1, times, again, it's the 3 right there. And then now that n is equal to 2, now what I'm going to have at the end, I've run out of s's. And so we're just going to have subtract the first derivative of that, which then I can rewrite, multiply that 2 times everything. So a couple of things that you may notice is, when we start, we have the y for both of these first ones. The s's get knocked down a step. And then for the first row, we always, after that point, the first one that we subtract is the initial condition with no derivative. And so you can kind of line it up. What I like to do is on my sheet of paper, I like to just go put all the rows. It's a Lego. Yeah. What class has the Legos? I got to figure that out. Teach it next year. Anyways, it does look pretty similar, right? It's just the s's kind of shift over 1. That's usually what happens. And we're just using all the same initial conditions in each column, and just it gets truncated each time as we have a lower derivative. So this is kind of our starting point. If I have initial conditions starting from the equation, I'm going to do this for every single term. And then from there, we're going to actually add them back all together like I have it in the equation. And we're going to solve for y. That's our goal here. It'll look similar to a transfer function, but the initial conditions put a lot more other terms in there in the numerator, which will take some time to try to solve for those constants. Questions? I guess 7 people, so hopefully no one else shows up. So this is where we're at. We're on the right-hand side. So if I have initial conditions, I'm doing Laplace transform. This Laplace transform, once I have that, I can solve for the final value. We talked about that last time. I can then take once I set it up and do partial fractions, I can take the inverse transform to find the dynamic response. So what is the actual, not just an approximation, what we can do up at the top, but the actual output function. That's what the Laplace transform can help us find. So we're going to do this example together. Don't worry. We're going to do this one together. This is example 8.6. We have an equation. So body has been done. We have values. We have initial conditions. The goal is to find our output if the input is equal to 4. Now, some of you missed the beginning class. Let me just go back a little bit. Here's the order of operations. Here it is. First, we're going to put it in standard form. Then we're going to take that differentiation. We're going to take the Laplace transform of every term using initial conditions. And then we're going to solve for y. And we put those all back together. And lastly, we're going to separate into partial fractions using the roots, poles, and bring it back to the time domain. So first things first, what should we do with this? Standard form. Nice. So to get it in the standard form, what should we divide both sides by? 2. Okay, great. So this is standard form, San Francisco. Y double dot plus 5 y dot plus 6y equals u. That's good? Why you look confused? Oh yeah, we should divide the other side by 2 as well. You're right. Okay, so here's my standard form. This is my standard form. And if u is equal to 4, what kind of input is that? It is a step. Yeah, this is a step of 4. If I plug 4 into that equation, this becomes 1/2 of 4, which is 2. So we are going to solve this for a, we have to have a specific input to be able to solve it. We need a number associated with it. And so we have the left-hand side, we've got the y double dot, 5y dot, 6y equals to 2. Yeah. Okay, now we're going to do the Laplace transform of every term. So I want to have it in standard form. We got it in standard form. We're going to do Laplace transform of y double dot. We're going to do Laplace transform of 5y dot. We're going to do Laplace transform of 6y. And we've got to do the right hand as well. We're going to do the Laplace transform of 2. So I like to just space these out row to row because there's a lot of similarities as we go forward. Why do I have to use this method? That's right here. I have initial conditions. So because I have initial conditions, this is the only place using this Laplace differentiation where I'm going to incorporate those in. So I must use this method. Questions so far? Okay, what should my first term be for y double dot? Very good. It's going to be s squared times y as a function of s. Because n is equal to 2. So that's my starting point. Everything after that is going to be subtracted. So now we knock the s's down 1. So we're going to have a minus s times my initial condition. No derivatives. And that should be it should be -1, yes. Now to end this out, this is either I look at this one, so I have s to the n minus 2, which that just becomes 0. So we have s to 0, that just becomes a 1. and I have this term, or I can use this. So this is made to handle, 100th order, whatever, where I end up with 2 minus 1, so the first derivative of the function. So you can look at that either way, whatever makes most sense to you. But we're going to still subtract it, so it's going to be minus 0.5. And so I can write this as s squared y plus s minus 0.5. Maybe I should do Superman s's, just so we don't confuse them with 5s, maybe? Anyone do Superman s's? You all had cell phones back in middle school and stuff, so you didn't have to just draw stuff. Let's do the next one. So I want to do y dot. The first thing I'm going to do is pull this 5 out of there. So I have a constant of 5. Now I can just say 5 times Laplace transform of y dot. So y dot is going to give me just an s times y minus, and we don't have any s's left. We're just going to use that right there. Notice how these line up, right? We're always going to use that first initial condition, no derivatives, just like that. And we see the s's get knocked down. Now I do want to make sure that I have the 5 there. So this should be a 5s times y plus 5. That is the Laplace transform of 5y dot using the initial conditions. Okay, I'd like you to, now we'll do the next one together. Probably should have had you do this one. What's that? Oh, cool. Okay, what is the Laplace transform of 6y? I don't have any. Yeah, it is. Yeah. I don't have any derivatives, so you can think of this as there's no derivatives. Therefore, if this is 0, you just have an s to the 0, which is 1 times the function. Or you just remember that, just like when I'm doing a transfer function, if I don't have any dots, I don't have any s's, right? But I still keep that y, so this becomes 6 times y. And now we're in the s domain, so I show it as y as a function of s. Okay, now I have my right-hand side, which is a constant. We had a step input of 4 divided by 2. So Laplace transform of 2. What is the Laplace transform of 2? We had an equation on the equation sheet. We have that Laplace table. We talked through some of them last time. If I have a constant, what is the Laplace transform of a constant? It is 2 over s. Thank you. 2 over s. See, that looks like a 5. I gotta do the Superman s or something. Draw 6 lines. Yeah, that's curvier. Okay, so 2 over s is our Laplace transform. Now, here's where I've done all the steps. I've used all the initial conditions. Why are we doing this? Well, our goal is to take that equation that we have, the standard form equation, and we're going to replace each of those terms with their Laplace transforms. So I'm going to take this first one, y double dot, that is s squared y plus s minus 0.5. That is my y double dot. So in the equation, we have y double dot plus 5y dot. I'm going to take that 5s times y plus 5. And then I have a plus 6y. So that's the Laplace transform is equal to, on the right-hand side, Laplace transform of 2 is 2 over s. So we're taking all those Laplace transforms we did, using the initial conditions, we plug them back into the equation, we replace it. And now our goal is to solve for y as a function of s. We should be able to get it all together and get everything else on the right-hand side. Anything not make sense? Anything that's confusing? The differentiation takes a little bit of practice. It does. Just to understand, how to incorporate that into your problem. But hopefully with this video too, as you're doing homework 5 eventually down the road, it'll make some sense. How would you like to solve for y? It's just algebra. So we're going to bring everything else to the other side. And then once, so I can bring the 5 over, the 0.5, the s, and that's going to leave me with, I can put it in brackets, we're going to have an s squared plus 5s plus 6 times y. So on this side, we'd have a 2 over s. We'd have a subtract s. And then I have a 5 and a negative 0.5. So that's a positive 4.5 over here. So we're going to subtract 4.5 on the right-hand side. So we do some algebra. Now we're almost there. Now, we've talked about having a good proper transfer function. We don't want to have fractions within fractions. So what I first want to do is get this to have on the right-hand side a common denominator. So everything's kind of lined up the same. And that way, when I divide both sides by this polynomial, it looks pretty good. So what can we do? Multiply both sides by s? Wait, right? Maybe? You can multiply both sides by s? Yeah. Yeah. So I can multiply this side by s and this side by s. You know what? I'll put that in a different color. Say, okay, we rearrange this, but to actually get a little bit easier, better formal transfer function, this is going to help. And so we can rewrite this as 2 minus s squared minus 4.5s. And I want to get that in order. So we're going to start with the highest order. So we've got negative s squared minus 4.5s plus 2. So that is on the right-hand side. If we multiply both sides by s, I've got this. Now I'm going to solve for y. It's going to be pretty easy. So y, now we can just divide by everything on the left-hand side. So my numerator is here. And my denominator is here. And that is my output in Laplace, in the S domain, this is what my output looks like. We talked last class about the final value theorem. This is where we could incorporate the final value theorem multiplied by S. And then from there, we can take the limit as S goes to 0. We can solve for the final value. That's a way to find it. But today's class, we can do that. But our goal today is actually to bring this back to the time domain to actually get a function. Like, what is the actual function of my output response based on a set of 4? So we use the initial conditions, we put this all together, we solve for y, the function of s, we get this. Now we're gonna look at the roots and kind of go from there. Questions? Okay. We're gonna pick up this again. I think I have a few slides maybe of where do we go from here. But if everyone's good, we can turn the page. Okay, we're gonna come back to this because we're halfway there. I have it all figured out in the S domain. It's just now a step to getting it out of there. So that leads us into the next part of today's lesson, which is called partial fraction expansion, partial fraction decomposition, whatever you want to say. What does that ring any bells? Like gong bells, just like danger kind of bells, warning bells, tornado sirens. Yes. Okay, partial fraction expansion. Partial fraction is the key. We were just stuck at y as a function of s. What do we do with that? This is the key to getting that to our time-based function. So what we're going to do is we're going to use the table on the equation sheet to set up those partial fractions. This is based on the roots or otherwise known as the poles. So if I can find the roots, this is where roots really come into play. They haven't yet already to set up my partial fractions. And so if I have distinct poles, basically I'm going to try to find some kind of constant for each of those poles. We're doing a partial fraction where we're adding up all these different fractions. We're finding those constants. And then once I have it set up like that, we can bring it back to the time domain easily. Now, there is a method. I'm not going to really go into it, called the residue method. This is something in the textbook. It works great for distinct real roots. When it goes to more complicated roots, I just think it kind of breaks down. So I'm not really going to teach this method. I'm going to teach it more based on using the table and the roots. But this is an option. If it's something that you're kind of familiar with, you can definitely use it. I just don't teach that method. But MATLAB can understand it, so it can help you find some of these constants when you're in the transform, you solve for y. All right, so roots, this is key to this. Here's our equation. We're actually going to use partial fractions to get this thing separated out based on the roots. And then we're going to bring it back to the time domain using the inverse Laplace. So as long as I can set it up somewhat similar to the right-hand part of the table, it will be very easy for me to bring it back to the time domain. What should we do first? Breathe. Should I make it? Say it again. Find the poles. Very good. The poles are the same as the roots. The poles are, if I set the denominator equal to 0, what values of s give me 0? This is a third order it's going to have 3 roots. What are those roots? I think it's just 2 and 3. -2, -3. They're actually not complex in this case. We'll get to complex soon. Is that right? Because you can break this down into a s plus 2 times an s plus 3. Now, if you can do it in your head, with this one, it's pretty easy. Other ones, I recommend making sure you know how to use your calculator to find those roots, because having a calculator do that, easier, not make mistakes, I think. So once I have my roots, this tells me a lot about how the system is going to respond. We've talked about root locations. I have a 0 root. That means that when I bring it back into the time domain, this is going to be like an a over s, a over 0. So we're going to try to find some kind of constant for my step. This is going to be like my final value. The other 2 roots are going to die out as time goes on. Oh, I see. Yeah. No, you did right. Okay. There are no i's. Okay, good. These other roots, just remember, the roots, the typical form is -a plus or minus omega I. For all of these, I don't have any i's. I don't have any imaginary terms. But these are just real roots. I have a -2, I have a -3. That corresponds with line 6. So notice line 6, this is the only one, well, besides this, if I have a repeated root, that would be line 7. But if I have a real and distinct root, that's my -a, so -2 or -3. That's what these roots tell me. If I have any omegas, I'm looking between 8 and 11, those lines. You know, if I have an a and an omega, I'm in these bottom lines. If it's just omega, I'm dealing with 8 and 9. So that's where the roots really help you. If I can identify the roots, now I know what my partial fraction should look like, because the way that we're going to set this up is I've got negative s squared minus 4.5s plus 2 over s times s squared plus 5s plus 6. Now we're going to set up partial fractions based on the roots right here. So I'm going to have an a over s. I'm going to have a b over s plus 2. So a 0 root gives me, 0 denominator here. A -2 root gives me 0 denominator here. Then we're going to have a constant over s plus 3. So the number of partial fractions should equal the number of roots we have. We have 3 roots. Therefore, we're going to have 3 partial fractions based on those roots. And we'll get to complex ones soon today. That's where we're headed. But now what do we do? I want to find A, B, and C, and here's why. Once I know A, B, and C, I just use my table. Those are the constants I have that I can bring back. Those will be the constants in front of these. That's it. So now we can bring it back to the time domain. We have our function. Problem is, how do I solve for these? You don't remember? Hey, and that's why let's go through it. How? Yeah. Well, the roots are still negative real because if I plug in -2 in for s, that makes the denominator equal to 0. So yes, a negative root should correspond with an s plus that positive number. So they cancel each other out if you set it equal to 0. Good question. So here's how we're going to do it. We need to get a common denominator. So to be able to add these together, I need a common denominator. So for example, a over s. If these are all supposed to equal the left-hand side, I need to multiply a over s by this polynomial over itself. So, which is also the same as s plus 2 times s plus 3. So this would be like s squared plus 5s plus 6 over the same thing. We're just multiplying it by 1. And then for b over s plus 2. I have my s plus 2 root. What do I need to multiply b by? It'll be s times s plus 3. So now, so far, this has the same denominator. This also has the same denominator. And then lastly, c is going to have to be multiplied by s times s plus 2. And so now I have all matching denominators. And one really important thing is why we always start with standard form. Standard form is going to give me a nice denominator here where I don't have to like divide stuff or anything. It's just all ready to go. So standard form is always a really great first step because now all of my denominators are equal. So therefore we can just look at the numerators here. We have a negative s squared minus 4.5s plus 2 is equal to as squared plus 5as plus 6a. So that's this, just multiplied out. We have plus bs squared plus 3bs plus cs squared plus 2cs. Okay, now this is a fairly, I mean, we're going to have more complicated equations than this. There will be higher order systems, complex numbers, everything. So if you have a TI, and I mean, I have $18 Casio, like it can do these as well. But anyone got their calculator out? You got a TI? Apps? You don't have any apps? Oh man. Wait, let me see. This one is a little bit older.
Last class that you were talking about, I didn't have it.
Polysimal too. Yeah. So TI, if you do apps, polysimal 2. This was the same thing as now. It's a slightly different one. Instead of the root finder, this would be simultaneous equation solver. If you don't have it, I mean, there might be a way for you to download it onto your calculator for sure if you have that certain I know those older ones, you had a different cable. But if not, I mean, it might be worth like asking your friends to borrow a calculator for the test that you know how to use, because this will save you a lot of algebra once you have this. So this equation solver, if you haven't used it before, basically I can look at the s squareds. So the s squareds, I have an a, so 1a, back up. I'm using this line above it to set up my equations. So I'm going to look at all the s squareds here. We have 1a plus 1b plus 1c is equal to, on the left-hand side, that's equal to -1. So that would be how I would set it up in my equation solver. And Casio, I can help you with this. Did you find it? It's into the same place as the root finder. I can show you after this. So that would be my s squares. For s, I have a 5a plus 3b plus 2c, and then equals on the left-hand side is -4.5. So that would be my second equation. My last equation would be just any kind of constants. So I have a 6a, and that's it. I have 0b, I have 0c is equal to 2. So, not quite. Wait. Oh, yeah, it is. Sorry. It is. So it's simultaneous equation. It would be 3 unknowns. Yeah. That's how you would set it up. So you do 1, 1, 1 equals -1. Yes. Okay. So now we can find a real fast with this one, right? A is equal to 1/3. Again, sometimes it's pretty easy. Now, again, even when I find a is equal to 1/3, then I got to plug it into here. I have 2 equations, 2 unknowns. You can do it just with standard algebra. That's totally fine. But we have most of you have the calculator with the skills on it. So as long as you know how to put it in, it's going to save you a good amount of time, and we'll have fewer mistakes. Good, theoretically. Doing a lot. I mean, it is something you want to practice with, yeah. We're trying to solve for the what's it say? So you just hit next. So yeah, you got 3 equations, 3 unknowns, and this is where you plug them in. So it usually pops up with x and z. Obviously you can correlate that to a, b, and c. So if I set it up like this, now I have my 3 equations, 3 unknowns we can solve with that function. Yeah. A constant. Yeah, I don't know if that's better. Constant, big C. Just all my constants right there. So again, you don't have to use a calculator. You don't have to use a calculator for any of this. I'm not going to require you to use a calculator, but you already have it. You might as well use it for this. So now, did anyone get the values? I know A is 1/3. I don't know if this one's smart enough. I don't think it's smart enough. Yeah. Anyone get other values? Cool. So if I go to the next slide, based on that, we should find that A is equal to 1/3, B is equal to negative 3.5, and C is equal to 2.17, or 6 repeating. Absolutely. Again, you can solve this by hand. You can use your calculator. I just want to point you to using some of those tools because it'll save some headaches in algebra. Once I have that, remember that we had A over S, so it was A over S plus B over S plus 2 plus C over S plus 3. So now I have those values, and we're going to bring it back to the time domain. So for example, so now we're going to do inverse Laplace. So inverse Laplace, now that I have it set up in a form, we can just use the table. So for example, y as a function of time equals A is 1/3 over S. So this is going to give me 1/3. B is negative 3.5. Now B is over S plus 2. So if I'm at the table right here, S plus 2, that A is 2. And so this becomes an e to the negative 2t. And lastly, we have C 2.17 times e to the negative 3t. So using your calculator, you can find those values. We can bring it back to the time domain. That is a thing. Questions? Okay, how can we check it? I'll give you one example. I have initial condition. Y at time 0 should be equal to -1. That's one of our initial conditions. Is that true? Well, from our equation here, this would be 1/3 minus 3.5 plus 2.16 repeating. Is that -1? That is? Great. You can do the same thing by looking at the derivative, and you don't have to. But this is just one way that I can check. Okay, I did my algebra. Maybe I could have made some mistakes along the way. Let me just check if that at least matches the initial condition. We can check it. And so it does match up. Basically, what's going to happen with this system, whatever system it is it's going to start at -1, and then it's going to climb up until it reaches 1/3. These are both going to die out over time. That would be our the look of our equation. So instead of having to approximate it, which approximation is pretty good, you can kind of get the ballpark of what's going on just by kind of drawing it out. In this case, we actually have the actual function for a step of 4. Okay. Huh? Is it break time? You know what? It's almost break time. In the same note, I want you to try to compute the inverse Laplace transform of this. Bobody has been done. Laplace transform has been done. We've solved for y. This is the last thing I want you to do, and then we'll take a break. So we have our system here. I want you to use the table. I want you to find the roots, set up partial fractions, and solve. This one will be even a little bit. Will it be? easier than the last one? I'm not exactly sure. I don't remember what the roots are. I don't think I have my notes to this. Oh, you know what? That is nice. Okay. So we got two roots. Based on those roots, you're going to set up partial fractions and you want to find your two constants. Once we have those two constants, we can just bring it back to the time domain. What are the roots? -2 and -6. They're real, not complex. I'm going to have an s plus 2 as one denominator of my partial fraction, and then a b over s plus 6. Now, if you have them switched, that's fine. We'll end up with the same answer. It's just different constants associated with other roots. Now just remember that these partial fractions have to add up to get the same denominator here. We want them to have the same denominator, so we got to kind of multiply by each other. So this would be like s plus 6 over s plus 6. This would be s plus 2 over s plus 2. So this is how we can get a common denominator and solve for those two constants. Anyone solving it by in their head? Did you get an A and a B yet? I think it's attainable. 1 plus 1 equals 2. 6A plus 2B equals 5. Now, obviously, you can solve for 1, plug it into the other equation. You can do that. Good. Yeah? Yeah? Yeah, great. Solve it in your calculator? Oh, nice. What's it? Yeah. It should be something, I think a negative. Actually, I don't have my notes, but you got a negative 1/4? Or a positive 1/4? Are both of them positive? What's A? 7? Oh, okay. Yours is, yeah. So from this, again, we can use calculator, whatever. We get 1/4, and B is 7/4. And so once I have it in this form, great. I have my two constants. I have it in the form that I like. It matches the table. So we're going to bring this back to the time domain. So therefore, we do the inverse Laplace transform. So y as a function of time is equal to 1/4 e to the negative 2t plus 7/4 times e to the negative 6t. How we use it. This is the final output equation based on whatever the step was. In this case, I think it's an impulse. Both of them die out, they go to 0. So it is right on time, 8:17. Do you have questions about this? I'll stick around. Let's take 5 minutes. So come back at like 8:22, and then we'll talk about complex groups. We're going to look at that. It's the same process. Now we're diving into those other fractions at the bottom. Yeah. Yeah, isn't it 2 weeks before graduation? I think it was 2 also. Yeah. Everything finished up around the same time, yeah. Well, the thing is, usually there's, is there a presentation after? Okay, I don't think so, but usually there's one like right before. You still turn in stuff after the showcase. You can, you can. There is, yeah, there is actually one last presentation. So some students, the stuff wasn't working at the showcase, but then they got it working a few days later for the final presentation. But why isn't the showcase the final presentation? I agree. Why isn't that? And then if it works, you pass, and if it doesn't, if it works, you get a medal. So, yeah, good. Yeah, we'll see what happens. Well, you haven't been all year. Yeah, just show that. I don't get it. Last year there was an MPK center, right? I think there was. I just don't know, like, how yours is different from theirs. Not okay. Theirs is purple though. Is yours purple? Oh, if you want a good grade, make it purple. That's step number one. You always paint it purple at least. The vending machine is it going to be? Oh yeah, I heard the payment process is kind of a holdup. Okay, that would be yeah. Tough. Didn't you buy a month subscription or something? And then cancel it? Okay, you can probably do that just for a month if you have a month left. Well, a month starting. This is showcase the 8th. Okay, so March 8th. That's like tomorrow. So as long as it can kind of work up until then. Isn't it? No, sorry. I'm thinking of, yeah, Saturday is 7th, right? Saturday. Sunday, okay. So, what? Okay. What? Oh, that last example that we had. Now, this is how you can find it in MATLAB. I'm not going to make you use it today, but I'm not going to ever make you use this. But in MATLAB, just like the way that we found it, we could find the residues, which are the constants associated with those. So that was like 1/4 and 7/4. This is a way that you could find those constants. So if you put in A, this is the residue value. So you can put in your numerator and denominator. It's going to spit out, for example, with this one, if this was our Y, so we put in our numerator, we put in our denominator, it's going to give you A1, which is 1/4. That is corresponding with the root 1, or the pole, which was -2. And then it would also give you this. So that's a way that, hey, once I have y as a function of s, I can use MATLAB to solve for those constants. So it can do that. Otherwise, we can use our calculator to find them as well. And yeah, I think it works decently well. So you can try that when you're doing some homework. Now, let's, for the case, now we don't see this too often, but let's say we had a repeated root. So I have a polynomial here. I can break it up. I have two of the same roots. I have a s plus 2 and an s plus 2 and an s plus 3. How do we set it up? Well, first off, the number of partial fractions should always equal the number of poles and roots. So we're going to use the Laplace table to set up the partial fractions. Because I had two repeated roots at -2, this would be the partial fraction expansion. This might be something that you remember from back in you're doing this in math class. But if I had it repeated, this would be like an a over s plus 2 squared. Then I would have b over s plus 2. That's how you handle repeated roots. Again, we don't really see it too much, but if you had a repeated root, that's the way that you want to solve it. Put these on the exam. Repeated roots. Jeez, I so far in the future. I usually don't. Usually I don't think they happen very often. So I wouldn't expect it, I guess. But what could be on the test? Someone asked if it was going to be on the test. I don't think so. But this would be our, based on this, using the table, we would get something like this. So we would have t times e to that root -2. So it would look a little bit different than what we had before. But usually our roots are either real or complex. So that's what we're going to cover next, complex roots right here. I'm not going to cover this. This is part of the textbook. I don't understand it as much. I don't really like the method, but that's the residue method. If you have repeated roots, not a fan. But let's say we have we solved it. We have y as a function of s here. Now we're going to talk about complex, because most of the time for a second order system, if it is underdamped, we are going to have complex roots. So we do see this quite a bit. Can anyone find real fast what are the poles of this system? What are the roots? And what is it? Sure, yeah. It's -3 plus or minus 4i. Wow, you did that fast. Okay, this is like my a term. This is my omega term. So typically, again, underdamped system, what's happening is that these roots tell us that it's going to oscillate, but it's also going to die out. It's going to be like an e to the -3t. So these are dying out while they're oscillating until they reach that steady state. So this is the response we expect. It's going to oscillate and then reach steady state based on those root locations. So how do we solve this? Well, again, the number of partial fractions should equal the number of roots. How many roots do we have? It is 2. Yeah, because it's a plus or minus, right? So I have my 2s plus 9 over s squared plus 6s plus 25. We're going to have 2 roots that we're going to set up. And how do I find that? Well, on the table, this is line 10. This is line 11. So the way that I want to set these up, because my goal is to bring it back to the time domain, I'm going to set up my partial fractions using these. So if I have it in that perfect configuration, I can find the constant and then bring it very easily to the time domain. So if a is equal to -3 and omega is equal to 4, let's set up our equation here. So omega is equal to 4. This is going to be a 4 up here. So I'm going to use this one over here. So I have some kind of constant times omega, which is 4, based on the roots. We have an s plus a, so it's s plus 3 squared, plus omega squared, which is 4 squared. So again, once you know the roots, you know what the partial fraction should be. In this case, I have an a and omega. There's a real part, there's a complex part, imaginary part. So that's how we're going to set it up. We're going to also use cosine. So because I have two roots, I'm going to have two partial fractions. Basically, my output, it is going to be sinusoidal, or sine plus some kind of phase angle. You could also say it's a combination between sine and cosine. And so that's why I'm using both sine. I'm always, for any kind of complex root, going to use sine and cosine as my partial fractions. That's how I get my two fractions to set up. So in this case, I would have a b times s plus a. A is 3. Then we have s plus 3 squared plus 4 squared. Now, what is the difference? I have my partial fractions now. Notice these have the same denominator. What do I need to change this denominator to equal the one on the left-hand side? Or are they equal? They are equal. Don't have to change it. That's great. And that's how it works. If I have this in standard form, if I have s squared by itself, there's nothing I have to do to change it. These equal that. That's the same thing. So this makes it really nice for me, because now I have 2s plus 9 equals 4a plus bs plus 3b. And you can almost do this in your head, because b is the only one with an s term. So therefore b is equal to 2. And what would that make a equal to? Plus 4a equals 9. Yeah, very good. So this would be 3/4. So my final equation, y is a function of time. A is associated with sine. So I'm going to now bring it back to the time domain. It should become something like this. This is 3/4 e to the negative 3t sine 4t plus 2, that's my b term, times e to the negative 3t cosine 4t. Again, it's just trying to set up our partial fractions based on the table so we can bring it back to the time domain very easily once I find those constants. Question? Okay. That's how we handle complex roots. It's just the bottom of that table. Now, there could be a part where we may not have an a term. It may just be purely complex. Then I'm just using sine and cosine. That's 8 and 9 lines from the table. So that's also a possibility. But it's all based on the roots. If I have a 6-order system, I have 6 roots. I'm going to have 6 partial fractions. I'm going to try to set them up based on the table. You know, if they have an a term, if they have an omega term, that's what we're going for. Questions? Okay. We're going to finish out class with 2 examples. I'm going to take a turn. You can, follow along with me. You can write it down, and then you're going to have a turn. Okay? You ready? We're on slide 23 of 29. Okay. Here's my equation. We have initial conditions, and what we're trying to find is our goal, which I guess it doesn't actually say, is we're going to try to find y as a function of time. What is my complete response? How will my system respond to an input? So first we need to put it in standard form. How do we put it in standard form? What? Oh, it is. Yeah, it is in standard form. We have initial conditions. So instead of making a transfer function, because I have initial conditions, we're going to have to include these. That means we're going to do a Laplace transform of every term. So I'm going to do Laplace transform of y double dot. I'm going to do a Laplace transform of, and I can pull the 4 out here, Laplace transform of y dot. So do the same thing for 20. We're also going to do the Laplace transform of the input side, and the input is actually 0. So I don't have an input to this system. So is everything just going to be 0 when I get to the end? Is y is a function of time just equal to 0? Why not? You just think like, can't be that easy. Now, why is that? Now, I don't have necessarily an input, but I do have initial conditions. So I actually have a starting displacement. So you can think of this as like if I have a mass spring damper system, for example, if I actually hold the mass, so I'm starting with a starting displacement of 2, and then I let it go, those are some initial conditions. So now we're going to see oscillation until we reach steady state. We should end up at 0 though, because at steady state, y steady state should equal 0. What is the Laplace transform of 0, by the way? Zero over s, 0, 0. It's just going to be 0. It is 0. Yeah. So Laplace transform is that. Now, this again using the equation sheet. I don't have it posted here, that differentiation equation, but it's going to be, if I have a double dot that starts with an s squared times y, then we always subtract going downhill from there. So I have an s times my first initial condition, which is 2, and then we subtract our final initial condition, which is negative 0.5. So this is s squared y minus 2s plus 0.5. Then for the next one, don't forget, we have a 4. Then we have y dot, so that becomes s times y minus, I don't have any s's left, but I'm going to use that initial condition. So that's 4s times y minus 8. And again, trying to get some practice with that differentiation, doing a problem. Lastly, what does 20 Laplace transform of y become? Just 20? No, that's close. 20y becomes 20y. So yeah, with no derivatives, there's no initial conditions included, but we got to have that y there. So now, using that initial equation that we have, we're going to plug all these Laplace transforms into that equation. So we get an s squared y minus 2s plus 0.5 plus my 4y dot, which is 4s times y minus 8. And then we have a plus 20y, and this is equal to 0. And so now we can combine all of the y's together, and this is what ends up looking like our transfer function. And everything else goes to the other side. So we have a positive 2s. We have a 0.5 and a negative 8. That's negative 7.5. So we can do plus 7.5 over here. And we get a very nice, I don't even have to worry about common denominators at this point. This is my transfer function, not transfer function. This is my y output function. Go all the way, we didn't start with whole body, but obviously whole body, if it's not done yet, we have to first get that equation. If I have initial conditions, this is where I have to include them here. So I'm including initial conditions. I'm setting it up. I put it all back into the equation. I solve for y. We're almost there. Here's y as a function of s. Now the next step is what? Our goal is to get it to the time domain. Yeah, let's find those roots. So the roots here, we have S1 and 2. You already found it? Wow, nice. Negative 2 plus or minus 4i. So they are, just like most of our underdamped systems, most of them are underdamped, we're going to have complex roots. So I set the denominator equal to 0. I can use my quadratic formula or calculator to find that. And so, because I have complex roots, I have an a term. This is my a. This is omega. I am going to set up my partial fractions using these two lines, just like I showed you on the last problem. Uh-oh. I don't have my answers. Guess we'll just have to solve this for real. Are you ready to go to the next slide? Any questions about this? All right, next slide, please. So we have a 2s plus 7.5. This is over s squared plus 4s plus 20. I'm going to set up two partial fractions using this. Now, we found the roots. So a is equal to 2 and omega is equal to 4. And so we're going to have a 4a over s plus 2 squared plus 4 squared. And then I'm going to use the line 11 to set that one up. So we're going to have a b times s plus 2 over s plus 2 squared plus 4 squared. And again, because I have it in standard form, these equations actually equal that, right? I have a 16 plus a 4, that makes 20, right? 2 times 2s, I have 4s. So those equations are equal. I just want to set them up exactly based on the table. So I have my omega, which is 4 times a constant. I have b times s plus 2. Those are all equal. So therefore, I can just look at the numerator. I don't have to do any common denominator changes. So we have 4a plus bs plus 2b. And again, b is pretty easy to find. B is equal to 2. And then a is equal to 2.5 over 4. 70. And again, I have multiple roots. Right now we're just dealing with 2, but if I had 3, 4, 5, if I have 5 roots, I have 5 partial fractions. So based on what those roots are, we would separate it. We'd have to find common denominators. But once I have them set up here, now I can bring it back to the time domain. So y as a function of time is equal to a, which is 7/8 e to the negative 2t sine 4t, plus 2, which is b, e to the negative 2t cosine 4t. So we're bringing those two equations back here once we find those constants. Is that those numbers right? They are, right? Yeah, okay, cool. And so this would, what happens as time goes on? Well, as time goes on, these both go to 0 because that e to the negative 2t. In fact, it dies out within 2 seconds. And so we will have oscillations. We will have, because we've got a sine and cosine, there's really like a sinusoid with a phase angle. But that would eventually die out at 2 seconds. So we see oscillation based on those roots with a final value of, but you got a different value? That's okay. Wait, I got 7/8. Oh. No, this should be s plus 2, s plus 2. Yeah. Questions? So again, this is going to oscillate. It's going to oscillate. Then at about 2 seconds, that's where we reach steady state because e to the negative 4 is basically close to 0. So after some oscillations, 2 seconds, now we hit 0. That's our final value. Also, like, you see all this stuff, circuit people, it's like doing all the same stuff. They got block diagrams, they got oscillations, they got standard form of first order and second order. It's like all the same stuff. It's crazy. What class? I'm not sure. I don't know. I don't really know. All right, here's your problem. This one's called your turn. Exactly. You can solve this in like 5 minutes. You're good to go. Motivation. Okay. Yes, exactly. It's different. So, hasn't yet ever been solved. No, I don't have any notes on this. I don't even know if it's possible. You what? Yeah, sorry, I was That's right. Even you should watch it. You can sleep from the self. Another thing you can do, once you, even when you solve it, you can check everything in MATLAB. I mean, you can check for the residues, the constants in MATLAB. You can check for the inverse Laplace transform. You can even check, kind of hard to do the differentiation, but once you have it in the S domain, you can check a few of those things. Make sure you're on the right path, and MATLAB, if it backs up what you get, that's pretty good confidence that it's done correctly. What? You're done? Oh, wait, what? Oh, sorry. Must have brushed it. Hey, before you get too far, what's the first thing you should do with this? Standard form, thank you. Because otherwise, you're going to have headaches the rest of the time, especially when you get to your partial fractions. So putting it into standard form will be very helpful. You want to get that y double dot by itself. So divide everything by 20. So this is standard form. Now, this input has a direct delta that stands for a unit impulse. So I'm giving it a quick hit, and then it's going to the input disappears after a very short period of time. How is our system going to respond to that? That's what we're trying to solve. And because we have initial conditions, we must use differentiation. We cannot just use a transfer function. you have questions, let me know if you want me to check anything as you're doing this. I don't really have an answer sheet, but I'm working on it. Yeah. Let's see, if you're bringing this over to the other side, that should be a negative 0.2s. And then, let's see, this is going to be together negative 5.2. So you're going to add it to that side instead of subtract. But otherwise, it's good. Do they? This, these are both negative 0.2s instead of negative 2. Yeah, that'll change a few things. Just in your numerator, though. Yeah. Okay. Yes. Yep. Yep.
Why does apply up here 1.5 instead of
Well, that's just the differentiation equation. The first initial condition will always be the one with no derivative. So, um, I mean, technically, this is also y dot. It's like y dot and y dot. that point.
Well, in this case, I'm hard to right, but this 0.5 would be 2, and that would be the negative.
No, we always want to use this first initial condition, no derivative. That's going to be that first column after the y. And then, yeah, for each one, s is just shift over 1. Basically.
Okay.
You based on the equation. Hey, so hopefully using differentiation and putting it back all together, we should be able to get to a y as a function of s. Then from there, you're going to figure out the roots, set up your partial fractions, and then try to bring it back to the time domain. This will also have two roots based on, because of the impulse that does not give us another s. So we should just have two roots, two partial fractions, two constants or residues to solve for. And that is done. So I have mine up here if you want to check if you've gotten to y as a function of s. From there, you want to find the roots. Who has the roots? Anyone have the roots? Yeah. Oh, that's nice. The roots are -2 plus or minus 3i. Think you're done? I don't have the answer. I don't know. Let's see. So this is good. That's good. This looks, wait, this should be positive. Huh. Because it's a negative 5.2 plus 0.4. So sorry, it's negative on this side. So you add 5.2 to both sides. So there should be a positive 5.6. That'll just change a little bit. Wait, you think you're done? Wait. Yeah, 5.6. Good. Probably good.
5.6 minus
Yes.
0.4 is 5.2.
Perfect. Wait. Wait. What? Hold on. This is positive point. So this is 5.2 equals 6a, right? Or no, 3a? Or wait,
Oh,
6a.
you're right.
Oh, hold on.
Yeah, it's divided by 6.
Hold on. This should be a s plus 2.
Why is it x plus 2?
I'll tell you why. If the roots are -2 plus or minus 3i. So a is 2. Our roots are always a negative a plus or minus omega I.
Oh.
So like because it's going to be negative over here, in the final equation,
I
right? Because
see,
it's dying
yeah.
out, it should be a positive. Yeah. So, yes, it'll change. Now B is not going to change, but your A term should. You fixed it? So B is negative 0.2, and A is just,
Is this still wrong?
wait, is A just 2? Is A 2? A is 1? Should just have 3A. 3A. Wait, oh, those aren't the roots. Wait. By 2, I see. I think it is 2. Yeah, because 6 plus, yeah, you're right. All right. Have one complete, very nice. You get out of here. Yeah, I'm gonna give you a little bit more time to try to finish this up. Try to, so once we're here, you find the roots, you set up. In this case, we're gonna be using again 10 and 11 because they are complex roots. And so from that, you're gonna find your two constants or residues, and then we can bring it back to the time domain. So we can actually solve for this function based on the impulse. I'm gonna put my stuff up as a reference point. I haven't yet solved it, but hopefully everything kind of matches up. And it's easy to mess up the algebra, but easy to mess up the algebra. So take your time with it. Try to make sure positives, negatives. If you have any questions, let me know. So close. Yeah. Nice. Yeah. So yeah, it's the same. Again, these are both my omega values. So 3 is equal to omega. A is 2. So we have this equation right here. And again, we can check, for based on the equation at time 0. So we can double check this. Did we do it right? One way that we can check is at time 0, sine of 0 is just equal to 0. So we get negative 0.2 because cosine of 0 is 1. And so that checks out. That is one of our initial conditions. It starts at negative 0.2. So there's ways you can check it. Again, just kind of taking your time with this. Now, we will look at a little bit more complicated, like once I have 3, 4 roots, right? I want to set up all those different partial fractions, so it is a little bit harder to keep that. That's why I was pointing towards like the calculator, using that to solve the equation instead of trying to. All right. If you have questions, you can stick around. If you want to finish the problem, if you got any lab questions, you can definitely work on that for the rest of the time. That is due Sunday night, and that's about it. Wow, enjoy your spring break. Just got to turn in that lab, and then you're good to go. We'll pick it up after spring break. And we're not going to have a test the Tuesday after spring break. How about that? I've heard of that before. It's pretty fun.